Okay, so here's some notes for 13.6 through 13.14 from physics, and really we're focused on two ideas. The first idea that we need to address is the temperature scale of Kelvin, or we call the absolute temperature scale. And so when we talk about units of Kelvin, okay, in the Kelvin scale, we have to come to the understanding that this was a scale where we didn't want to use any negative numbers. We wanted to talk about 0 being the absolute lowest that we could go. And so what we find is that absolute 0, and this equates to when the particles of air or matter, mass, different atoms, you know, they all have this vibration that they do, and depending on how much energy or temperature they have, they're vibrating larger or more violently. As we slow them down, we get to a point when there's no longer even vibration within the particle. And so when we talk about absolute 0, we're talking about the fact that there is 0 movement inside that particle. And so absolute 0 is a very, very theoretical thing that we try to find ways to approach, because there are those questions of what happens when you get to that point. But for what we're going to work with today, we're just going to talk about this idea of heading towards it, or how do we convert to it in terms of working with the ideal gas law. And so the absolute 0, or 0 Kelvin, okay, is equal to a negative 273.15 degrees Celsius. And so it's important that you understand that when you're converting temperatures, that if you want the Celsius temperature, you need to add or subtract 273 from your, or add 273.15 to your Kelvin temperature. If you have 10 degrees Kelvin, you add 10 to negative 273.15, and you'll get your negative 263.15. So that's how you'll convert to getting Celsius temperatures from Kelvin. Now, if you want to go from Fahrenheit to Kelvin, or Kelvin to Fahrenheit, totally doable. I personally just say switch from Celsius to Fahrenheit, or Fahrenheit to Celsius, then make your conversions. Don't go straight from Fahrenheit to Kelvin. But that's because I'd rather work in the world of degrees Celsius and Kelvin. Fahrenheit is really antiquated when it comes to dealing with scientific problems. So that's the first thing you need to understand, is how to make those conversions. The second thing that we start to talk about is what we call the ideal gas law. Now, we need to understand that this is the gas operating under ideal situations. The reality is we're incapable in almost every case of creating these ideal scenarios. But this does give us an expectation without any energy loss of what should happen. So we know that this will never be perfect in our man-made world, but this gives us an idea of what's about to happen as we deal with some specific changes. And so what we find out from the ideal gas law is that the pressure times the volume, okay, so the pressure times volume equals little n, capital R, T. Now there is another version of the ideal gas law that deals with molecules. We're going to specifically deal with the version that has to do with moles. So a couple of things we need to understand up here. In this version of the ideal gas law, pressure needs to be measured in newtons per meter squared. So I can't say that I've got 7 atmospheres of pressure. That's a lot of pressure, but it's not a number I can use. I need to have that in newtons per meter squared, or pascals, okay? Not in atmospheres or millimeters of mercury. It's got to be in those standard units. The volume needs to be measured in cubic meters, which we would kind of expect. Meters times itself 3 times, that's our cubic meter. The N is a number of moles of a gas. So it depends on how much you have. We're going to convert it into moles, or that'll be given to us how many moles of a gas that we have. R is a set constant. And that set constant that we're going to use there, okay, is 8.314. Oops, 314. And if we looked at its units are really just whatever units it takes to cancel everything out. And so if you look at pressure times volume over here, you have Newton over meter squared times meters cubed. That would be the equivalent of newtons times meters, or Newton meters. Over here in our nRT, N is moles. Okay, so you have moles. And then T is temperature in Kelvin. We're going to get to that in a second. So over here, we'd have to be able to cancel all of that, end up with like Newton meters per mole times Kelvin. You know, these units are just end up being leftover units or whatever it takes to cancel. So I'm not going to worry too much about that. But the temperature, because of the way this ideal gas law works, needs to be in Kelvin. Okay? If it's not in Kelvin, then we end up with negative pressure volume values, which doesn't make sense. And so, because the lowest pressure that we can experience in an absolute sense is 0. We can say that there's a negative pressure comparison between two places, but the pressure in this gas shouldn't be less than 0. So we expect all these things to be positive. Okay, a couple things. When you have a container of gas, so maybe that's a balloon or a flask, and you've closed it off and you've sealed it, there's no change to the mole value. And so think of it like we trap the gas. Well, N won't be able to change if we trap the gas. And R is a constant, so it can't change. When we hold the gas amount, the quantity or the moles of gas constant, we end up with a variation of this that ends up looking like this. P1 V1 over T1 equals P2 V2 over T2. And what this allows us to do is to talk about a gas before and after some changes to its pressure, volume, or temperature. If I take a balloon full of gas, okay, and I put it out in the cold, in the snow this overnight tonight, I'm going to come out and I'm going to notice that it's smaller, that its volume has decreased as the temperature has decreased. I might also notice a change in the pressure, how firm the balloon is. If the balloon's smaller, maybe the pressure also dropped. And so there are different things. Maybe the pressure increased. Maybe it's firmer because I can't squish it as much because it's already so small. And so what we notice here is that this becomes a very solvable problem. Key idea here, though, this does give us some flexibility. Because N and R are no longer in the problem, what we have is a pressure equal to a pressure, a volume, and a temperature, and a temperature. Temperature still must be in Kelvin. But in terms of pressure and volume, if I'm using, liters on the left and I use liters on the right, those units would cancel. And so it ends up not mattering what unit I choose to use there, as long as I'm consistent, which also allows me to use things like ATMs for pressure. And so this gives us a lot more flexibility when solving. A lot of these problems are going to give you, 5 out of the 6, and there's a couple of things that you have to know to be able to work with these ideal gas law problems. Is that they're going to give you a couple of, they're going to reference this one idea of STP. They'll talk about there being a gas at STP. That STP stands for standard temperature and pressure. So we're looking at a specific temp, which is 0 degrees. Was it 0 Kelvin or 0 Celsius? Mr. Welch, pay attention. Which one are you using? At STP, that should be 0 degrees Celsius, which is 273 Kelvin. Now, of course, we have our 273.15, but bear with me. And then standard pressure is 1 ATM. Now, those are not guaranteed to be the situation. I mean, 0 degrees Celsius is not necessarily the most common temperature in Idaho. but it is the standard that we're all going to go back to talk about our comparisons. And so when we talk about STP, it just gives you a locked-in temperature and pressure. Notice it does not lock in the volume. That depends on how much gas you have. The more gas you have, the bigger the volume in order to hold a 1 atm pressure. Okay, hopefully that's enough to help you understand the ideal gas law and conversions with Kelvin. Good luck, and we'll see you in class.